Hello everybody, welcome back. I want to tie up some loose ends from section 4.2. We actually covered, I would say, half, if not more, of this section in the previous video. So for the first bit of this, expected value and variance, let's just say recall, and let's just do a little bit of a recap. For continuous distributions, or continuous random variables, I guess would be the better way to say that. If I wanted the expected value, we do it the same way. We still take our values the random variable can take times their probabilities, except now we have a probability density. We have those functions f, and then I add them up, except now we have this continuum of possibilities, and so instead of summations, we don't do that. We have to integrate. And then we have to integrate over everything, although, as we've seen, very often our distribution is defined in a way where these bounds actually are bounded. They're numbers, because my distribution function here becomes 0 at some point. And so that very often simplifies for us. And then, because the algebra rules that I can do with regular sums still apply to integrals, we showed that, or well, we talked about it, we didn't really show it, that if I want the variance, I can actually still use this formula to get the variance, where if I want expected value of some function of the random variable, so say like my expected value of x squared right here, that is going to be the integral over everything, although maybe those bounds simplify, of whatever that function of x is. So in this case, that would be x squared times its density. And so I would have to find that, also find the original expected value here, using just an x times that density. And then I can use this same formula to get my variance. So we can calculate expected value and variance in the same way we have before, except now instead of regular summations or adding things up normally, we have to integrate. Now, from that, I want to move on and talk about cumulative distribution functions. And now let's say recall for discrete random variables, let's just say random variables, the CDF, the cumulative distribution function, which we call, let's say, big F of x, was equal to add up for every value the random variable can take up to that x, the probability of taking those values. So for instance, if I had my coin flipping example or something, so say flip a coin twice, x be number of heads, then my probability function looked like, well, I can either get no heads or 1 heads or 2 heads, and the probability of getting no heads was 1/4, probability of getting 1 heads was 2/4 or 1/2, and the probability of getting 2 heads was 1/4. Well, my cumulative would be probability of getting no heads or less is still, well, that would just be probability of getting no heads, so 1/4. Probability of getting 1 heads or less would be, well, there's a 1/2 chance of getting 1 heads and a 1/4 chance of getting 0, which is less, so then we would have 3/4 there. And then the probability of getting 2 heads was 1/4, and getting less, we already had the 3/4, so I would add that on. In other words, once I get to that highest possible value, my cumulative function gets up to 1 and then stays there for any number thereafter. So, in other words, the cumulative distribution function, which we call big F, is equal to the probability that my random variable takes a value less than or equal to that. And so maybe I should have used a different letter or something. And this is still the definition. So still the definition. In continuous random variables. In other words, for a continuous random variable, when we start using integration, we use integrals. For a continuous random variable, the cumulative distribution, which we'll call big F, is defined by big F of x being the probability that we take a value up to that number, which means I'm going to integrate, I'm going to take all my values less than or up to whatever that particular x value is, and then I look at the probabilities for all those values less. Now, I've already used my letter x here, so I need a different letter to plug into that function. So let's just plug a different letter in there, and then that would be fine. And so let's do an example here. And in particular, I want to steal an example from your WebAssign homework. So this is WebAssign homework 10, number 3. Now let me write down, we're going to do something a little bit different with this example. I want to actually find the cumulative distribution function, which is not what it asks you to do directly in that problem, but I want to show you how that's useful. So let me write down our probability function. So it gives us this. Now in the problem, it doesn't write it this way piecewise like I have, but it does say that, okay, the probability density function looks like this when x is bigger than or equal to 1. So we're assuming that means, oh, it stays 0 until I get to 1. And now I want this cumulative distribution function, which is not what it asked for in this problem 3 of this WebAssign homework, but I wanted to go ahead and show you all that. So let's see what we want here. So my cumulative distribution function is going to be this big F of x. And, well, if my original density function is just sitting at 0 until I get up to 1, so here's x equal 1, the area underneath, remember we're integrating, is going to stay at 0. I'm not getting any new area yet. And so my cumulative distribution function is also going to stay at 0 until I get up to 1. And now we need to integrate this thing. So starting at 1, my cumulative distribution function is going to start doing something like this. Or not my cumulative distribution function, sorry, my density function is going to jump up and start doing something like this. And my cumulative distribution function, we actually want the area underneath up to some point. And so maybe I should choose a different letter here. And now let's figure out what that is. And so what we want is we want the integral from everything off to the left, but it just stays 0 until I get to 1. So I really can start my integral at 1. And then I want to go up to some place, let's call it x. And I want to integrate this density function right here, except now I want to use a different letter because I'm integrating up to x. So I want to plug maybe a y or whatever and use that as my variable in my density function there. So we're integrating that 0.65 e to the minus 0.65, and then in parentheses we had that variable, which I'm going to switch my variable inside to a y. We had that y minus 1 in parentheses, and then instead of saying dx, we'll say dy. That way I can actually use my x as the variable that will be the variable in my cumulative distribution function. Now one of the reasons I wanted to do this is that not all of our Cal 1 classes are going to talk about derivatives and antiderivatives for these exponential functions. So let's review that very quickly. So the derivative of, if I just have an e to the something power, is just itself. In particular, that means that if I want to take a derivative of e to some number times x, then the chain rule says, well, that just stays itself, and then multiply by the derivative of the stuff inside. The stuff inside is what's up in that power of the e. The derivative of that is just the c that's on the x, and so that number will pop out. Oop. And so what that tells me is that if I want to do an antiderivative of e to a number times x, then I need to undo what the derivative does. The derivative takes whatever number is on the x and the thing gets multiplied by it. It pops out in front. Well, if I want to do antiderivative, I would need to undo that, meaning that my e to the cx here would end up getting divided by whatever that number was on the x, and then plus constant, however you want to do it. And so when we're doing these antiderivatives, these integrals, we have to remember that integral rule for the exponential functions. Okay, so back up to where we were. Let's go ahead and try to do this integral here. So first off, I have integral from 1 to x. Let's simplify this power in here. So we have 0.65 e to the minus, let's distribute that minus 0.65. So we have minus 0.65 y, and then minus times minus is going to give me plus 0.65 times 1, so plus 0.65. And then I still have this dy hanging out inside that integral. Now, this is e to a power plus a power, right? If I have something to a power plus a power, that's the same thing as, whoops, that something to the one power times that something to the other power, right? So what does that tell me? That tells me I can rewrite this as 0.65. This e to the 0.65 I can write that times the e to the minus 0.65y. And then this is just a constant. E, remember, is just 2.72 blah, blah, blah. It's one of those weird numbers like pi, but it's just a number. And so it to a power is just a number. So that's a constant that I can pull out in front. And so then I'll pull that constant out in front along with this 0.65 here. Altogether, that's just a constant. So I can pull it out in front of my integral. And now I want integral from 1 to x of e to the minus 0.65y dy. And we have a nice antiderivative rule for e to a number times my variable this time. So that means if I want to do this integral, we now know how. I'll have that constant times, now what's my antiderivative here with respect to y, of course. So this is going to become e to the minus 0.65y divided by that minus 0.65. And then we're going from 1 to x. And so I'm getting 0.65 e to the 0.65. And now plug in the x. So that would be, I'll pull that minus right there out in front. So we're getting minus e to the minus 0.65. We're plugging in the x now. So x divided by 0.65. And then minus, now we plug in the 1. Well, that would just be e to the minus 0.65 times 1. So now on top we're going to get e to the minus 0.65 times 1. And then on the bottom, we had this minus again, so that's going to turn my minus there into a plus, and then I have 0.65. Now I can factor out a 1 over 0.65, and then that would cancel with this 0.65 here, and so that cleans things up a little bit. I have e to the 0.65 times we had minus e to the minus 0.65 x, and then plus e to the minus 0.65. And now, remember, what can I do? If I have e to the 0.65 times e to the minus 0.65, I have the same base to different exponents, but I'm multiplying. We would just add those exponents, right? So that means when I distribute this e to the 0.65, the 0.65 power there is going to cancel that one off, and it'll be e to the 0, which would just give me a 1. And so we're getting minus e to the negative 0.65x plus, remember, add exponents, 0.65, and then this times this is just becoming a plus 1. And so we're getting 1 minus e to the negative 0.65x plus 0.65. And then if I wanted to, I could maybe clean up that power a little bit and say, pull out that 0.65. And if I factor out a 0.65, I'd have minus x and then plus 1. And that would give me 1 minus x in the power again. So the format is matching quite nicely with the way we were given it originally. So that's my integral. And so what does that mean? That means our CDF, our big F function, is still 0 until I get up to 1. And then once I get to 1, it starts becoming this function here, which we had as 1 minus e to the 0.65 times 1 minus x. Now, let's actually look at what the problem is really asking for now. So let me write that down. Okay, so first it asks us, what's the probability that my random variable takes a value less than or equal to 3? And if you're able to compute the cumulative function, what's really nice about that is that by definition, that's my cumulative distribution function at 3. And we have a nice formula for that right here. Plug 3 into the x, and then so that would mean I have 1 minus e to the 0.65 times 1 minus 3, which would be 0.65 times negative 2. So I would have e to the minus 2 times 0.65 would be 1.3. And for the second part here, you have to use a calculator to figure out what that is. For the second part here, I have the probability that x is bigger than 3. Now my cumulative distribution function gives me values up to 3, so it's not as direct. However, x being bigger than 3 is the opposite, so this will be 100% chance minus, or 1 minus the probability that x comes out less than or equal to 3, which means I want 1 minus my cumulative distribution function at 3. And so I would just get 1 minus that same number I found up here, which of course 1 minus 1 would cancel out. So let's see, 1 minus e to the minus 1.3. 1 minus 1 would cancel out, and then I'd have minus negative, so plus e to the negative 1.3. And so it would just come out as whatever that is. Use a calculator. And then in part C, it asks for what's the probability that my random variable comes out in a value between 2 and 4. Now again, your version of this problem may be different than the one I got, but in my version it was something like this. So how would I do such a thing? And the trick here is that my cumulative distribution function, say here's my density function, the actual original probability function. My cumulative distribution function, let's say my big F at 4, or not my big F at 4, let's just say this is 4. my cumulative distribution function is giving me this area all off to the left from that 4. Now, normally when we look at antiderivatives, we define it as the area from 0 up to whatever number. But here we're using our antiderivatives as that area all the way off to the left forever. And that's going to be defined, though, because these are probability functions. The total area underneath has to be 1, so we know that that'll converge. Anyway, my cumulative distribution function at 4 is giving me this area. And then if I look at the cumulative distribution function at 2, it's going to give me the area all off to the left from 2. And so if I just subtract that off, I'll get the area in between, which is that probability I want. So I would say, oh, well, this is my big F at 4 minus my big F at 2. And then I could just plug into the formula that I found for my cumulative distribution function and say, oh, well, that's the 1 minus e to the minus 0.65 times 1 minus 4 minus that 1 minus e to the minus 0.65 times 1 minus 2. And then that's just going to simplify. 1 minus 1 would clear off. And then I have negative e to the stuff minus negative e to that stuff. So these two are going to become positive. So I'd have a positive e to this over here, which would be negative 1 times the negative 0.65. So e to the 0.65 minus e to the minus 0.65 times negative 3. So that would be 0.65 times 3. And then, of course, you'd want to use a calculator, figure out what number is that. Now, there's one more thing I wanted to go over real quickly that's in this section that I think is of interest, and that is the idea of a median, which median is not the same as mean, which is what we were calling our expected value. Median is middle value. In other words, the median, which let me denote with maybe an M. The book uses a mu with a little tilde over top, is, let's say, the number where that probability of being less than it, that's supposed to be an M, is exactly 50%. In other words, half of your area is on each side of that number. So now this doesn't have to equal the expected value. For instance, I could have a distribution, say, that's skewed to the left. It has this long tail off to the left, and then my stuff's most likely right around here, and then like nothing happens off to the right. What that would do is these sort of extreme outliers that occur way off to the left are going to pull my original expected value down, but they won't have much effect on where the middle value is. So my median, my middle value, might actually be higher than the expected value. And now this definition, again, what's the probability that x comes out less than or equal to a number? Well, that would just mean that big F of that number equals 50%, or 0.5. So if I'm able to find my cumulative distribution function, do that integration with the x still in it, if I'm able to find that cumulative distribution function, then I can just set that formula with an m plugged in for my variables equal to 0.5, and then solve for that m, and I'll be able to find medians, which is pretty nice. And so I wanted to point that out, that you can find medians, and it's not hard once you know what your cumulative distribution function is, and that the median does not have to be the same as the mean, the expected value. They can be different. Anytime you have a distribution that's, one, not symmetrical, but in particular if it's skewed or something like this, then most likely those two numbers will be different. Anyway, I think that's a pretty good place to stop. Thank you.